the top left of your screen there. This is Baltimore, and I'm kind of zoomed in from a Google Earth image on the whole city, and you can see it's quite variable. That's probably not a surprise to anybody here. The cities are quite variable. They have different land cover types. Also, take a look at the NLCD land cover data set that we have there. We're pinpointing two separate neighborhoods in Baltimore with divergent morphology characteristics. One of them is very, very urban, very developed, not a lot of trees, very small lots. And the other one, Howard Park, is quite large lots, lots of trees. And this can have really important implications for the neighborhood themselves, but also how the boundary layer develops in the city itself. So that's the problem. How are we going to solve that? We're planning to deploy two large eddy covariance towers along with a sonic anemometer turbulence tree, as I'm calling it. So I have a schematic of what the tower is going to look like there on the right for you, and an actual picture of a tower that we have not in Baltimore. This is a tower in Indianapolis. Jason Horn, a speaker later on here, actually took this picture. Because one of the major problems that we've had with this system, and maybe other systems as well, is just actually deploying it has been a humongous hassle due to permits and just legal constraints and just permitting and et cetera. Not the kind of problems that you might expect if you're used to operating on, campuses or private land, which some of these often are, or national parks. So these towers are yet to be deployed, but luckily we do have some samples of what we might expect to see from two very, very similar urban tall tower systems. If you look to the bottom left, what you're looking at here is a diel plot of energy fluxes between Site 7 and Site 3, which are actually very good analogs for what we're going to see in Baltimore. I could prove that, but I don't have the time or space on this slide to show it. But basically, you can see the net radiation is about the same. That's pretty good. They're all pretty close. And the real differences in between the two systems is between the latent and the distribution of energy between latent heat and sensible heat efflux. That really has implications for land surface temperature, which is with this talk could have easily been in the heat session a couple months ago. As you can see on the bottom right, land surface temperature has a drastic difference in between the two neighborhoods, probably largely due to the vegetation concentration. But there is some outlying effects that aren't explained by the internal urban morphology. But also, trying to bring this back to an air quality talk, I think the most important, we're not measuring air quality directly at either of these sites, but we do have colleagues as part of this project doing urban air quality. Really what these things can try to do is try to get an understanding of why is the urban boundary layer doing what it's doing? Why is it growing the way it's growing? And what drives those dynamics? Because basically boundary layer dynamics are going to govern air quality inside the urban kind of bubble. So that's the goal of what we're trying to do here. And I think I'm out of time, so I'll stop there.
Thank you so much, Benjamin, for your great presentation. Next is our second speaker, Shao Chen from St. Louis, the Washington University in St. Louis.
Yeah. Hi, everyone. Thanks for the introduction and nice talk, Ben. I'm Xiaoyu Chen, and I'm the third-year PhD student from Washington University in St. Louis under Professor Jian Wang's lab. I'm currently working on the urban climate, especially looking at the lake breeze effects on the urban environment in Chicago using data from a network named the Microsoft Eclipse Network. Oh, next slide, please. As you can see from the left panel, the pink shaded area, Chicago is one of the ozone non-attainment area, which has very severe ozone issue together with some other North Lake Shore cities. But there are a lot of field campaigns already being conducted based on this severe air quality issue, especially from the Milwaukee, Sheboygan, these cities. And the researchers connected the heavy ozone issue with the wind from the lakeside, which means the lake breeze would worsen the air quality in the cities. As the right figure shows the time series of the ozone and the wind direction, and also together with the pollutants Rose figure, we can see that with heavy pollutants, the wind always from the south side, which is basically from the lake side. But based on this situation, there are only a few limit research conducted at Chicago. So my research is aiming to check this effect on the Chicago at an intracity level. Next slide, please. Yeah, my research is basically based on a network named Microsoft Eclipse Network. This is a local sensor network. It installed over 100 sensors across the city, like under the bus shelter in the figure shown. It collected several parameters like the temperature, relative humidity, and some meteorological parameters such as the and some pollutants like the PM 2.5, ozone, nitrogen dioxide, etc. And it has very high resolution of both from temporal and spatial. It collects data for every 5 minutes, and it has over 1 year, 1 whole year data. Based on the next slide, please. This page shows our result of the lake breeze effects on the several parameters, and this page shows the difference of the situation under lake breeze compared to non-lake breeze. With darker blue, it shows more darker blue color, it means the more decreased situation, and the more red means the more increased situation. From the first row, we can see that lake breeze significantly decrease the temperature and also mitigate the haze index inside Chicago. It also shows a very clear spatial distribution with the onshore area. It shows more decreased, and inland it shows relatively lower decreased. And on the other hand, it have a very important role for the air pollutants. For example, it increased the PM 2.5 overall, and but on the other hand, it just decreased the ozone level inside the Chicago. And this trend is very different from my previous introduction that other observations from other cities, they said the lake breeze normally will get increased ozone for the city. But we can still get a lot of explanation for this situation. For the ozone, it's because the severe local emissions, severe local pollutants of the ozone mixing ratio. So the cleaner lake breeze will bring cleaner air into the city and dilute the ozone mixing ratio. Finally, will make the air quality better. So based on this, that's my introduction for my research, and it also indicates the importance of such mesoscale wind pattern or mesoscale weather system can influence a lot for the coastal city areas. Yeah, thank you.
Thank you so much, Sean, for talking about the air quality in the Cocos area. Our third speaker is Evelyn. She is from UT Austin. Evelyn.
Hi, everyone. My name's Evelyn. I'm a fourth-year PhD student at UT Austin, and I'll be telling you guys about some of the work we've been doing in the Beaumont-Port Arthur area. So Beaumont-Port Arthur is home to a very dense concentration of industry. And so naturally, there's a lot of emissions and odors that nearby communities are often exposed to. So if you take a look on the left here, the top left, this is a map of sort of the measured odor activity. And this was derived using odor detection thresholds for hundreds of different chemicals that we measured in real time with our mobile measurement van that you can see there on the right. So we did a lot of passes and measurements around the whole area to try to understand how individual sources contribute to the local air chemistry. And additionally, we compared with models from other members of our team to try to understand how these contributions are affecting the regional air quality. And the reason this is important is because, a lot of these communities might not understand what they are being exposed to on a daily basis. So it's very important to understand with local meteorology and, maybe if the wind direction changes one day versus the next, you could see contributions from a number of different sources. So we're aiming to get a really good idea of how these industrial sources affect the odors and pollutants that people are exposed to. And hopefully we'll be able to share with the community and develop some responses to help maintain public health. So.
Thank you so much, Evelyn. Now I would like to introduce Jason from BSEC. He will talk about his research. Jason, please.
Yeah, let's just tail off what Evelyn said. So, right, in order to get the transport of these constituents correct, you need to know something about the actual flow field that's going to be driving this transport, right? And so what my work does is I've actually really deal with the surface layer turbulence side of things in these urban areas. And so largely, and it's really hard to get away from in any sort of numerical modeling framework and things of that nature, the rough wall boundary layer logarithmic wind profile is often assumed. And it's assumed to hold in these urban areas in a lot of these numerical models as well. And there's a suite of assumptions that go into this very idealized boundary layer formula, right? And you can see I've got that pictured here on that top left, my left panel. And there's two length scales that are associated when you set up the lower wind profile here, this logarithmic wind profile. One is the displacement height. Basically, it's the height you need to displace the profile in order for it to hold. And there's another one called Z naught. That's the roughness length, which is a characteristic length scale associated with the objects on the ground. And so there's really two ways so right, these are two important length scales. If you're going to set up this wind profile correctly, you need to get these length scales correct. So there's two real common, actually there's three common ways to estimate these. One is a rule of thumb where you basically say the objects on the ground are this high. So we're going to assume these parameters are roughly this value, right? You can go a little more in depth and you can actually get into the morphometric realm of things where you say the actual geometries of the objects, the standard deviation, the frontal area exposed, et cetera, based on those numbers of the objects on the ground, you put them into an empirical formula, you can estimate what this Z naught and ZD probably should be. These are based largely on large eddy simulations and wind tunnel experiments over like cuboids, kind of like what you see there in that picture of the morphometric with the arrow pointing there. The other one is the anometric method, where you basically assume that similarity theory, which is the theory of surface layer turbulence under this exact same suite of assumptions, holds in these areas. And based on observations from an anemometer, like a sonic anemometer, you can back out what these anometric or what these aerodynamic parameters should be, right? So you're kind of implicitly assuming that this is holding there. So actually piggybacking exactly off of that flux tower that Ben showed a picture of earlier, down in the lower left, these are results comparing observed mean wind speeds at the height of the tower compared to what the Monod-Nabokov similarity theory is estimating. And so the Monod-Nabokov similarity theory is essentially just the logarithmic wind profile with a stability non-dimensional function attached to it. But in the bed, it's just another way of setting up what stability dependence impacts on this logarithmic wind profile. And you see there's a systematic bias going on here, right? And this is not unique. So why should we care about this? Because this is not unique. This bias with increasing wind speeds, you're getting a larger deviation from what the theory should be and what we're actually observing. Because again, like I said, this is literally in all the numerical weather models. You see it in not just our observations in Indianapolis, you see it across the board. I've looked at a ton of different turbulence measurements from all sorts of different areas. You see this exact same thing kind of coming up. And then you look at measurement and model, like WRF model comparisons, you often see they report that there is a systematic underrepresentation of the mean or overrepresentation of the mean wind speed in these urban areas. And that's probably because they're using the similarity theory. So the punchline is that none of these Z0 or ZD really work depending on whatever method you use. And it's largely because the similarity theory is probably violated in these sort of situations. And so that's a big thing of why is this happening? How can we fix this, remedy this, implement into models, right? So that's kind of the going forward sort of thing here.
Thank you so much. Now our last speaker, Robert.
Yeah, so this is kind of continuing upon the boundary layer turbulence that a previous speaker was demonstrating. So basically, the convective PBL height, in models, it's a representation of how high air is mixing from the surface, particularly with the boundary layer in the morning. A lot of times during a clear air scenario, when it's clear out, you'll get the rising the boundary layer height will rise throughout the day as you get diurnal heating of the surface, as you get these turbulent eddies coming up from convection. Now, this is a lot of times used as a metric to evaluate the structure of the planetary boundary layer in clouds. And particularly if we're in more stable, if the planetary boundary layer is more stable, if we have a capping inversion, this, for example, could actually cause some air quality issues with, for example, if you have aerosols being trapped at the surface, this could cause some elevated PM levels. And what I'm looking at here is more how these PBL height retrievals are performing, not when we have some of these poorer air quality issues. For example, in Chicago, we had wildfire smoke events during the summer that we could take a look at. And what we have at one of our observation sites, we had a co-located Doppler lidar and ceilometer for 4 cases of Canadian wildfire smoke in Chicago. And what the Doppler lidar retrieves, it retrieves not just the backscatter, but it also retrieves the vertical air motions. Meanwhile, the ceilometer just retrieves the backscatter. So the Doppler lidar gives us extra information about the amount of turbulence that is present in the boundary layer that we cannot get from the ceilometer. And we find for different estimates of the planetary boundary layer height that the Doppler lidar retrieved planetary boundary height in these wildfire conditions better represents the characterizes the evolution of the convective PBL, because it is able to get these vertical motions. And like with the ceilometer, where the signature of the PBL is often masked out by the wildfire smoke that is present over the area. So in conclusion, some of what we've been finding here is that this actually can give us some indication. If we're able to improve these PBL estimates, these wildfires, it can help how these weather forecasting models and Earth system models handle the boundary layer processes and mixing in these wildfire cases so that we can improve our prediction of air quality over these areas.
Thank you so much, Robert. So this is the end of our presentation. Now I would really like to invite Dimitris to actually give a very short synopsis of all of the talks. Then we will open the floor for questions from the audiences. Dimitris, please.
Thank you everyone for the great presentations. We saw basically a combination of observational and theoretical work, starting with flux tower work from BSEC that Benjamin presented, that connects really well with the work that Jason did regarding the canopy parameterization and the roughness and displacement thickness, basically parameterization in urban areas. Then we have Xiaoyu going through the Microsoft sensor analysis in Chicago and what it means in terms of interaction with cities, air quality with lake breeze. And then we had also Evelyn talking about the emission source and composition and odor activity in the Vermont Port Author area, and the work that CITEX IFL does. And finally, we had Bob, who presented the observational work on the effect of Canadian wildfire smoke on the boundary layer metrics. Now, I would like to open the floor for questions. And since we are waiting, please go ahead and type any questions you may have. But as we wait for this question, I would like to ask Jason and Ben some questions regarding the synergy. Like many of the mesoscale models like WRF or E3SM, I know that E3SM has a kind of experimental version of urban canopy parameterization in general. Those typically include schemes like building effect parameterization that already takes into consideration the mixing length variability based on urban canopy schemes. So I was wondering if your work tries to improve those, or it's more like towards the fundamental research on turbulent boundary layers and the surface layers interaction.
Yeah, let me grab this really quick. So essentially, my work had initially, it came from the fact that I had these really awesome high resolution LiDAR data of all the buildings. And I knew that these sort of formulations had been proposed based on the building geometry, and we had these observations on the field. So I said, well, let's first test them because it does still have significance, right? The building effect parameterization in WRF does try and impart drag and other sorts of things to the TKE, and maybe the log profile is not as, or the single layer urban canopy model kind of assumes an exponential decay based on the geometries there too. But I still said, well, in a lot of other cases for, let's just say like larger, like climate models and or numerical weather models, this is kind of just assumed to hold a lot of the time. So it doesn't have completely irrelevance, and it is just largely assumed even to some degree at the bottom here. So it kind of came through that. My work now is moving towards evaluating a lot of those urban canopy models and comparing them to those anemometer trees that Ben showed to evaluate the actual statistical representation and the building and energy parameterization of WRF LES run with it, and how well it can create the wind profile in the canopy compared to what we observe out in the field, right? And it could do completely terrible because at the resolution I'm running it, where you have roughly less than like 100-meter resolution, I'm down to 37-meter resolution. You've essentially violated all of the assumptions in the urban canopy model, where you assume the canopy is infinitely long and there's a canopy in both buildings on sides and everything. But still, as we begin to push towards these higher and higher resolution simulations, where we continue to still use this canopy parameterization until we want to analyze how well it does, and then two, exactly what you said, begin to then advance it, push it forward, then yeah, there's still a lot of work to be done. So you're exactly right. It's a great question to ask. And that is something, as far as potentially developing and interrogating the performance of the canopy model, is of a lot of interest to me, and kind of what I'm doing right now. I'm wrapping up a lot of this work that I showed up now. And I didn't get into a lot of the nitty gritty. I actually have ideas of why the similarity theory is probably failing and what we could potentially do to incorporate those things into parameterizations. But only so much time. Yeah, that's a great question though. Sorry, Ben, I didn't mean to completely like steal that and run away with it.
No, that's perfect. That's your area. So well done.
Yeah.
What I'm gonna answer that question with a question. I don't know anything about an updated ELM urban canopy model. Who knows more about that? And what's up?
Yeah, we are heading towards that, improving basically the parameterization in terms of E3SM as well as WRF. In Crocus, we have been working, and we had a whole field campaign on collecting data and validating basically an improved parameterization for street level dynamics. And basically, we are in the process of wrapping up the work and publishing it. This is more like on urban canopy physics things, but we have seen implication for air quality, temperature, of course, and everything, because you modify basically the eddy viscosity at the interface, which then ends up having implication in many things, including heat or air quality.
Perfect. Thank you. Looking forward to hearing more about that.
Yes. I was like, since we're still waiting for questions, I want to ask a general question for everyone. Like, I know we have been collecting a lot of air quality and flux measurements across different IFLs and air quality measurements. Is there a plan to do an either comparison between cities like Chicago and different other cities in the US, and see if for example, the lake breeze effect mimics the characteristics that we see in a coastal city, or how other cities air quality is affected basically by local peculiarities. And this goes to all of you. Do you see some, we saw really nice results from multiple locations. Do you see the potential to actually have a synergy and work all together with a comparison study, basically? And this is open to all of you.
Yeah, I think that's a very great idea. Like when I look at the lake breeze effects on Chicago, I reviewed many like previous research for the sea breeze or bay breeze effect on other cities. That includes the Baltimore, which is part of IFL project. So I think it will be great if like there are some like city together to examine the air pollutants or the meteorological parameters changing under the breeze from the lake or even from the sea, from the bay. We probably maybe see some differences or maybe see something in common, but that will be all great.
There is I'm sorry to jump in, Dimitris. There is a great questions from chat from Kirsty, and I think his question is for all of the speaker. Maybe if you guys want to give a short insight, everyone, if you like that. So the question is, I think you can also say that, or do you all think will be the best case insight about urban air quality and atmospheric processes in a new way? So speaker, maybe you can start talking a little bit if you want it. Anybody wants to jump in?
The thought here behind this question, folks, while you're thinking about it, right, is that I don't know anything about urban air quality or urban atmospheric processes. I love to hear you guys talk. And to me, it seems like there's reasonably obvious synergies between, you know, the new data from the flex towers and the new data from the observational campaigns, the new modeling techniques. But I'm not enough of an expert in this field to really understand how in the best case scenario, how might this change our understanding of sort of urban air quality, or urban atmospheric processes, or you know, something else cool that you guys are excited about, you folks.
Yeah, I can say something here. I think the most exciting avenue forward really is related to what you were saying about some intercomparison between cities. We've done a lot of different studies across the country, and it's interesting to get, you know, insights from a new place. You might find, you know, different aspects of cities that share similarities. And additionally, I think with the inner IFL approach, you know, we have a lot of complementary research, but also instrumentation. So sort of combining our efforts, I think, will be helpful to yeah, just sort of find new and innovative ways to address air quality in urban spaces.
Yeah, I want to just make a note on Demetrius's thing and kind of play into that too. You know, as a young academic, early career, watching the IFLs is really awesome in the fact that it brings all of these interdisciplinary fields to one large conglomeration. But what I've also noticed is it's really hard too at the same time, because we all speak different languages and we've got to kind of cross those boundaries. And so I've been kind of stepping back and watching the more senior scientists navigate this and trying to glean what I can. But from what I've noticed is that it's really tough. It's really, really tough. And it actually makes progress much slower, right? And I guess I've seen people get frustrated by that to a degree. But I think it's just the reality of it in answering these really hard-hitting, awesome science questions where you kind of are trying to cross these lines. So yeah, I would love that there'd be inter-collaboration, but I feel like there's difficulty in itself in the cross collaboration on a single IFL, to where I think it would be difficult to do, but it should happen. It should happen, right? Yeah.
I think one of the ways I think that might happen is, when all the IFLs are releasing their data and all their different measurements at the end of the, as part of the campaign, it could be a follow-on study that could be funded using the data sets that we provide to do an intercomparison. Because then you probably at least you have a team of people, probably even from each IFL, looking at those data sets on a proposal. Be like, oh hey, we as a follow-up proposal, we look to compare the measurements for these 4 IFLs because we want to see how the fluxes and all the air quality and all the different turbulent mechanisms differ between the 4 cities. That could be one avenue to take that.
Absolutely. And on top of measurements, I think it will be important also to see modeling results being shared and bring them in a way that everyone can have access and compare, contrast the different cases. That's definitely, I think, would be extremely beneficial for the synergy and probably solving more, even more important than big picture questions.
I'll just jump on that. There is, I know of an effort to do that exact thing. I think, and they have a little bit of funding to do so. It's a cross IFL proposal, specifically focused on improving urban models. And it's sort of at this point mostly a discussion group of like, what are you doing? What and how are you solving this problem? But there is some effort that way already.
Are you talking about the land service model stuff, Ben?
Yeah, that
Okay.
Ben.
Yeah.
Not me, Ben.
Different Ben. There's
Who's
lots of
leading it?
Bens.
Ben Solman.
Yeah.
Solman's leading it, I believe.
Ben, we have a question. Like, would you like to talk a little bit more on the impact of urban morphology on turbulent fluxes when cities are in different climate zones, like Phoenix is in desert, for example?
I can talk, but uninformed, in an uninformed way, I can.
It's totally
talk.
okay. I'm just wondering, even I don't have any idea. I just wanted to get any kind of thoughts on that. But I really appreciate that. Please go ahead.
Yeah. So there's these tall type flux towers are actually, they're very difficult to do, so they're kind of rare. That's one thing. There's not a lot of data for a lot of things. But I think the main difference that we're seeing at our sites is in the vegetation concentrations. And so if you don't have a heavily vegetated city where maybe there's not much vegetation variability, even within population densities, you might not see the same differences that I am hypothesizing here. But there is, I've gleaned a couple of graphs off of people from different conferences. I know I've seen some types of fluxes from shorter type statures in Phoenix and things like that. And this is where a cross comparison across city, the assumptions that and learnings that we make from Baltimore or Chicago or wherever do not apply across different climate zones. They are absolutely not universal. You have to take the background climate into account. We have another sort of related project, I didn't show it here, looking at short stature grasses, these turf grass, like lawns, everybody's got, golf courses and cemeteries and things like that. The type of signal that we see on the East Coast and even in the Midwest and Indianapolis is just not at all what you see out West.
Thank you so much. I actually have a questions to the Shao Chen from about the air quality in I think the Chicago area. So
Sure.
like I'm just curious to know, like when you mention about significantly mitigate heat stress, I mean, so actually I'm just curious to know, are you actually meaning the heat stress definite is you are also including the temperature with the relative humidity, like the heat index or the mean radiant temperature? You are
Yeah,
referring to that
yeah.
one or just the temperature? Just
Yeah, actually in my result page, there are two figures. One is for the just the temperature, air temperature, and another one is the heat index. That heat index is calculated based on the air temperature plus the relative humidity, and also it has some like minor adjustment when the relative humidity is extremely higher or extremely low situation. Yes, that's a calculation result. So like in the lake breeze condition, since the relative humidity is basically increased with the breeze coming. So the heat index that change, that decrease the level actually is not as much as temperature, since relative humidity partly compensates the comfort from the cooling air. Yeah, it's
that's
basically, yeah. It's probably it's easier to understand like another way. Like when you get into a hot but humid air condition, you may not feel comfortable. But if although it's hot but it's drier, maybe you feel much better. Yeah.
yeah, exactly. That's the thing in
Yeah.
Phoenix. Otherwise, it would be impossible to live in the Phoenix area. We are really in the desert city, but the humidity level is not that high. So we are kind of lucky to still living over here and can survive. So my the kind of related query is this the pattern is based on the like the aggregated for the day and the night time, or do you think we might see kind of different pattern in the day and night time? So do you have any thoughts on that? Like the conclusion you are getting from, is this based on the diurnal cycle or just
the lake breeze often happens at the afternoon during the daytime. So the result I shown is 3 hours duration after the lake breeze. So it's basically it's about like 5 or 6 p.m. at the Chicago local time. So that's basically on the daytime.
That's cool. Thank you.
Sure.
Can I ask a question? Oh, you go ahead. You go ahead.
Oh, okay. Thanks, Demetrius. I actually want to follow up on what you were saying earlier about the challenges for inner IFL. I agree it might seem very challenging. Everyone has their own foci, but I also think it's the best thing that happens to all these IFLs. There's so much overlap in what we are doing, but also there are specific edges in each of those inner IFL. And like, for example, Evelyn was talking about this very unique way of looking at compositions of odors, or for example, those flux towers that you guys were talking about. And this is really, really super cool. So just to share what we are doing, for example, we leverage observational capabilities and modeling. Plus, we take from some of you from BSEC, for example, but also happy to work with others, indoor modeling and outdoor measurements with other instruments as well. So I think it's not too late to collaborate, even like all connections are not possible, but even some of the connections that are being made are very valuable for this whole project. Sorry, go ahead.
No, that was a great point. That is a great point. Because in the end, I think something will come of this. Whether that comes within the remaining time frame of the projects, unclear. But I do think something is going to come up. You have these awesome cross collaboration, like again, like you said, investigating a lot of the same questions. So It would be silly not to. And you see this a lot of times with our European colleagues. They're kind of really on top of this sort of thing, as far as the intercomparison across cities and stuff like that. I had a question for Evelyn. So we do a lot of community outreach and things like that. How does that go over with some of your work? Because yours is super pertinent to a lot of the community members around there. How do they receive this kind of things? How do you go about telling them about this?
Yeah, so part of our team is actually dedicated to just that. So they've been leading a lot of like task force meetings, meeting with community members and asking them what their specific concerns or questions might be. And actually that's been informing our measurement campaigns moving forward. So actually just 2 weeks ago, we wrapped up another measurement campaign where we aimed to go to different places and try to profile the air quality during different wind patterns, where the community specifically had mentioned that they had the highest concerns. So those tended to be, in communities that were really close to some of these sources. Maybe there's some community members themselves that actually live in those neighborhoods that are close by. So it's been really helpful just to hear from even people on the team that live in the area as well, like, oh, like I smelled this over there, or oh, there's been historically like a lot of emissions from this site. So it's a really fun experience to get to hear from a community member and then drive out and then we measure it and it's there and it's like, oh, this is exciting. We're gonna be able to have some things to share with them and try to understand better what it is that they're actually being exposed to.
Hi, I've got a question. So do any of you actually do much actual explicitly resolving of buildings and that sort of thing, or is everything that you're all doing is using kind of the larger, more regional scale models like WRF or that sort of thing?
I do both dynamic downscaling with WRF to sub 100-meter resolution when you have a statistical representation of the buildings, and also work on building resolving and canopy resolving simulations of the flow field at sub-meter to meter scale.
Okay. What are you using to do the
ladder? Yeah, Palm typically. Palm is good. We have a few other things you could use. Fast Eddy. It's not quite as coupled with or easy to play with it, but yeah, Palm is typically what I do, and they're working and they're currently about to release a way to offline couple Palm to WRF and use WRF as a forcing, so that you can use an actual, hopefully downscaled mesoscale thing rather than just like a constant pressure gradient, et cetera, kind of thing. Yeah. Yeah. But it's not too bad to actually get in. There's a lot of good resources out there for it, for learning Palm. Demetrios, is that what you use as well?
No, like in Crocus, we use a combination of an in-house, like NEC 5000, NEC RS, actually, the GPU version of NEC for building resolving.
Yeah.
And our colleagues from Notre Dame, Joe Fernando, and Sen are using OpenFOAM.
I thought I had seen some OpenFOAM work come out of that too. Yeah.
We use basically the forcing from WRF to basically develop some meter resolution simulations in CCAR. Yes.
Yeah. How's it going, Demetrios?
Great. Always nice to see you, Matt.
Good to see you too.
Okay. Any other question? Well, yeah. With this, I would like really to thank again all the speakers for the great discussion. Thanks, Ben, Xiaoyu, Evelyn, Jason, and Bobby. And thank you everyone for the very fruitful discussion, and hope to see you again next month. where we will have our discussion on health determinants and indoor air quality. Again, thanks everyone, and see
Thank you guys too, the conveners, for putting this together. Yeah, thank you very much for the opportunity. Yeah, much appreciated.
Thank you everyone.
Yeah, yeah,
Thank you.
Thank
Bye
you,
bye. Good day.
everyone. Right.
Thanks.
Thank you,
Thank you.
everyone.